Okay, folks, I think it's about time. Welcome back to Chaos Seminars. I'm very glad that we have here today Professor Quek, who is a distinguished member of the Center for Advanced 2D Materials. Fantastic work in a theoretical approach to 2D materials. And she has been well known for her work on ab initio studies of 2D materials. So today she's here to tell us a tale, a fairy tale of materials in the flatland. So we're looking forward to hear about this story. Swing, thank you so much for coming here today to be with us. Looking forward to your talk.
Thank you very much, Antonio, for your kind introduction and for your invitation. And thank you to all of you for making the time to be here today. Let me share my screen. Yep, here you go. So today, as Prof. Antonio said, I'll be taking you through a tour of what I call fascinating flatland, and I'll be giving the tour from a first principles perspective. So we live in a 3D world, but in this 3D world, there exist materials of multiple lower dimensionalities. For example, we have molecules and quantum dots in 0 dimensions, carbon nanotubes and DNA in 1 dimension. And of course, in 2 dimensions, we have graphene that was awarded the Nobel Prize in 2010, as well as other 2D materials that have been experimentally synthesized and isolated in recent years. And electrons that live in these lower dimensional materials experience quantum confinement effects. And as a result, the properties of a material depend strongly on the dimensionality of the material. In this talk, I will focus on the chemistry and physics in 2 dimensions. So before we begin the tour, let me tell you a little bit about the methodology that we use in this work. When we say first principles calculations, we refer to calculations that predict the properties of materials using quantum mechanics and starting from information about the atomic constituents. We don't have any empirical parameters, but we do make some well-defined approximations. And the workhorse of first principles calculations is Kohn-Sham density functional theory, which was also awarded the Nobel Prize in 1998. And with density functional theory, or DFT for short, we can get reasonably good ground state total energies as well as qualitative features of the band structure. But to get quantitative features of the band structure, we need to go beyond DFT using many-body perturbation theory and most commonly in the GW approximation. So one of the main projects in my group is to develop approaches to obtain the band structure more quantitatively, looking at energy level alignment at large interfaces. And for that, we develop approximate GW methods. So let me begin the tour using an example which I feel illustrates one of the classic examples of physics in 2D, which is quantum confinement. So here are some as a picture of a 2D metal that is well protected by graphene and is grown by my collaborators in Penn State. And the 2D metals, they form a quantum well. And we know from quantum mechanics that electrons that are confined in an infinite square well will have quantized energy levels. And the energy levels are inversely proportional to W squared, where W is the width of the well. So as W decreases, the energy spacing between these levels increases and the interband optical transition energies increase. So we computed the interband optical absorption peaks in these 2D confined metals, and we obtained values of 1.2 EV for 3-layer indium and 1.7 EV for 2-layer indium. And they match well with the experimental peaks from ellipsometry at 1.2 EV and 1.8 EVs. Now, if we plot these peak positions against the width W of the well, we can see that the peak positions increase as W decreases. And the relationship goes like W to the minus 1.3. So that's a clear quantum confinement effect, but the effect is reduced compared to the infinite square well. And the reason is that the wave functions are not completely confined in the 2D metal, and in fact, states involving the topmost silicon carbide substrate layer will also contribute significantly to these interband optical transition peaks. So in our next stop, I will talk about a 2D transition metal dichalcogenide, or TMD for short, which is a semiconductor instead of a metal. Now here we have a picture of the bulk H-phase TMD. We have inversion symmetry in the bulk, and as a result, the bands at the valleys K and minus K, or K prime, are spin degenerate. But what happens when we go to 2D? In the monolayer case, the inversion symmetry is broken. So as a result, we no longer have this spin degeneracy at K and K prime. And in fact, the spin at K is the opposite of the spin at K prime for states with the same energy. We also are able to selectively excite excitons at either K or K prime using circularly polarized light. And because of the coupling between spin and valley, this has given rise to a very exciting field of valleytronics in recent years. Now, what happens when we apply a magnetic field to these materials? In general, there are two effects. The first we have is the Zeeman effect, where the energy levels at K and K prime shift in opposite directions. And this is quantified by the single band G factors. Besides that, the block states will also reorganize into quantized Landau levels. And experimentalists have been very interested in probing the effects of magnetic fields on these 2D TMD materials. And there are some open questions. So the first is, previously derived Landau levels were asymmetric in K and K prime, meaning that the expressions that we would use for the Landau levels at K are not exactly the same as the Landau levels at K prime. And many researchers have gone on to add the Zeeman term on top of these expressions. But the question is whether it is appropriate, and some have argued against this practice. Another question is, what are the effects of many body interactions on the single band G factors? So to address these questions, we developed a first principles approach that treats the Landau levels and the Valley-Zeeman effect on an equal footing. And we use a general Hamiltonian instead of a model Hamiltonian, which allows us, therefore, to actually use different approximations to this Hamiltonian and compare the results from DFT and from many-body perturbation theory in order to get insights into the effects of many-body interactions. So here are our results. For a 9 Tesla magnetic field on monolayer WSE2, which is a prototypical TMD material, these horizontal dashed lines are the Landau levels. Now let's focus on the Landau levels at C1 and plot these as a function of the magnetic field strength. We can compare this plot with the data extracted from recent gate-dependent reflectance experiments, which probe the Landau levels at K and K prime separately. What we see on the vertical axis here refers to the critical charge densities that are required to fill the Landau levels at C1 and is determined by the onset of Pauli blocking. So if we compare the theory and experiment, we see that the agreement with experiment is actually pretty good. The solid lines are the GW levels and the dashed lines are the DFT levels. So many body effects in GW actually increase the magnitudes of the G factors, and that in turn results in slightly improved agreements with experiments. And in future work, our work that's already ongoing, we are interested in looking at the interplay between many body interactions and charge doping as well. Okay, next I move on to another story in Flatland where we introduce some visitors in the form of molecules from 0 dimensions. And these are mixed dimensional heterostructures. Organic molecules can enhance the properties of 2D materials in various ways. At the same time, organics and 2D materials can together be components of functional flexible devices. So the first example that I will give belongs to the first group. We have my collaborators in Yale have synthesized a new DMAP OED molecule, which is a strong donor molecule. And when single layer MOS2, a TMD material, is functionalized with these molecules, the current voltage characteristics change significantly and the current goes up by orders of magnitude. And this effect is again related to the 2D nature of the material because it has a large surface area to volume ratio. And in our calculations, we find that each molecule donates about 1 electron to the 2D material, and the highest occupied molecular orbital is spin split and pinned at the Fermi level. So in other examples, both the molecules and the 2D material are active components of a potential device. So for example, in this case, we have COPC molecules on magnetic VSE2 layers, and we predict the existence of spin-dependent tunneling barriers. So that's potentially useful for molecular spintronics and quantum information. In other examples, we also have potential photovoltaics from pentacene molecules on MOS2. Now, in these examples, the alignment of energy levels across the interface are critical for the device functionalities. So for example, in spintronics, we do need to have spin-dependent tunneling barriers, while for photovoltaic applications, a type 2 energy level alignment, as shown here, is needed for charge separation. Now, experimentally, it can be challenging to determine the energy level alignment. Some of the challenges include the requirement for low temperature or fairly large, high-quality samples. It is also not easy to perform in situ characterization of the atomic structure at the same time. So first principles calculations play a role here because they are able to draw a relationship between the atomic structure and the energy level alignment, or ELA for short. And we can also provide details of the physical and chemical mechanisms that govern the ELA. Now, to understand what goes into the ELA, let us revisit the interpretation of energy levels. So here I show you a benzene molecule. Now imagine we bring in an electron from far away onto the benzene molecule, then the energy of the molecule is going to change. So the LUMO level, lowest unoccupied molecular orbital, relative to the vacuum is exactly the negative of the electron affinity, which is the energy gained by the molecule when an electron is added to the LUMO. The same can be said for the highest occupied molecular orbital, or the HOMO. Okay, we start with a neutral molecule, and we remove an electron that is already there to infinity, and you leave behind a hole. Then the minimum energy required to do that is the ionization potential, and that is the HOMO level relative to the vacuum level. So the easier it is to remove an electron from the molecule, the closer this HOMO level will be to the vacuum level. Now the question is the HOMO-LUMO gap going to be the same when we put the molecule on a substrate? The answer is no, because electron screening from the substrate will stabilize the added electron or the added hole. Here, I show a picture of the charge density response of a 2D semiconductor TMD to an electron perturbation that is just above this layer. The blue color here shows a depletion of electron density, and this is a manifestation of electronic screening, which we know also from classical physics. So this electron screening makes the whole system more stable. So by stabilizing the final states, it becomes easier to remove an electron or to add an electron to the molecule when it's on the substrate, and therefore the HOMO-LUMO gap will decrease. So we have already seen that the intrinsic gas phase HOMO-LUMO gap, as well as the screening from the substrates, will help determine the energy level alignments. But besides that, there's also screening from other molecules, effects of interfacial dipoles, as well as interfacial hybridization. So all in all, these different effects actually make it quite difficult actually for theory to predict the ELA as well. So density functional theory with the standard approximations for the exchange correlation functional typically would underestimate the gas phase gap by several EVs. And this has led to orders of magnitude errors in the conductance predicted for single molecule junctions. Improvements in these functionals can lead to a bigger HOMO-LUMO gap, but typically do not account for environmental screening effects. And more recently, efforts have been made to account for screening from bulk 3D substrates, but not from other molecules or from 2D material substrates. Now, many-body perturbation theory, the GW approximation, does provide a firm foundation for us to predict these levels, but they are computationally challenging for the large interface systems we are interested in here. So we want to have a predictive and also tractable approach for the energy level alignment. A simple approximation that works for simple cases of small molecules physisorb on substrate is what we call the DFT plus sigma approach, where we start with a DFT level alignment and we correct that in 2 steps. Now, sigma here refers to the corrections to these energy levels that are due to many body effects beyond DFT. So the sigma here has 2 parts. One will be the gas phase correction, which we can get quite easily with GW or other approaches. And then the other approach, the other part, is the effect of the substrate, which we can get using an image charge calculation or a generalization of that where we compute the screening response of a substrate from first principles. Now, using this approach, we can compare our results with GW calculations, which would be our benchmark. So we can see that if you compare these two, the results are not too bad. And I also want to point out that the gap for benzene can be reduced quite a lot when placed even on boron nitride, which is a very wide band gap 2D layer. So it goes from 10.5 EV to something like 8 to 9 EVs. So this illustrates the importance of screening on the level alignment in these interface systems. Now, this approach that I have mentioned here takes into account the gas phase gap screening from the substrate as well as interfacial dipole effects at the DFT level, okay, but not screening from other molecules or interfacial hybridization. So for molecules that are larger, which are more polarizable, and for systems with interfacial hybridization, we need a more general approach. So we're going to work towards an approximate GW approach, a many-body perturbation theory approach. And in this approach, a reasonable starting point is always a DFT calculation. And we calculate, again, what we call sigma, which is a correction to these levels due to many-body interactions. Now in GW, the W refers to the screen-Coulomb interaction. And to compute that, we need to calculate this quantity here, which I'll call chi. And calculation of chi is usually the bottleneck for us in terms of memory requirements and computational costs. So other groups have actually worked also on approximate GW approaches to the level alignment problem, and they have typically focused on very weakly coupled van der Waals heterostructures with no interfacial hybridization. And these approaches, they have two things in common. First, they use what we call the add chi approximation, where the chi of the full system is approximated to be the sum of the chi's of the two components. And the second thing they have in common is that they compute the self-energy using wave functions of only one part of the interface, the part that they are interested in. Now, what we did that was different was that we realized that it is quite easy to see that this add chi approximation works when there's no interaction at all. We are able to show that in fact, the approximation also works in the presence of interface hybridization to form bonding and anti-bonding states. And it works up to first order in the overlap and Hamiltonian overlap matrix elements. And this finding enabled us to develop an approach that also works for hybridized interfaces. And we call this the XAFGW approach. It has 3 steps. The first step involves calculating the chi matrix for each part of the interface, and we can do that using only a very small unit cell and then expanding that to the supercell by an unfolding method. The second step is where we do the add chi approximation, and the third step, we call it full sigma. We use the full wave functions of the interface if hybridization is important, and this takes into account hybridization effects. So our only approximation is in step 2, and step 1 helps us to save costs. Now, to make sure that our approach works, we did a benchmark study on bilayer black phosphorus where we have prototypical bonding and anti-bonding states. And you can see from the band structure on the left that our XAFGW approach here reproduces the results from a regular GW calculation. So this shows that add chi works even with interface hybridization. We also wanted to see when the approach would stop working. So we considered the band gap of hexagonal boron nitride on graphene, and starting at equilibrium distance, we moved the 2 layers closer together. And surprisingly, the XAFGW approach works quite well all the way to a distance of almost half that of the equilibrium distance. If you look at the one in purple, which is XA no FGW, here I do what the others have done in the literature, where we use the wave functions of the boron nitride layer only in computing the self-energies. And you can see that it works well at equilibrium, but it fails as hybridization increases because the wave functions are changing. Okay, so now that we have established our approach, we use it on PTCDA, a PTCDA monolayer on WSE2 monolayer that is supported on graphite. And we have our experimental collaborators, Prof Andrew Wee and NUS, have some beautiful STS data on this. And if we compare our results in red with those from the experiment, they actually match very well. The ones in blue are from DFT, which is a much poorer approximation. So this is a large system by GW standards, and it's possible because we only use this small unit cell here to calculate the chi matrix. So moving on to a different system, we consider COPC on VSE2 monolayers. And this is an interesting system because it's a mixed dimensional magnetic heterostructure. Now, transition metal phthalocyanine molecules, they are very popular with experimentalists. They are stable, they're scalable, and they're tunable, and they also have potential for spintronics and quantum computing. But one problem that we face is that the spin on these molecules, at least for COPC, it tends to be quenched when placed on bulk metal substrates. So the questions that we had were, is the spin on COPC going to be retained or quenched on VSE2? And are there spin-dependent tunneling barriers? So our DFT calculation shows us that the spin is retained on COPC, which is good news. And if we want to look at the tunneling barriers, first I show the DFT, density of states, for COPC on VSE2. And you see the HOMO and LUMO here, they are spin degenerate at this level of theory. Now to do better, we want to do some GW calculations. So first we need to check that we are, I want to add that the DFT HOMO-LUMO gap is 1.4 EVs, which is the same as the DFT gas phase gap as well. Okay, so we want to do GW calculations, and to do that, let's first check what happens in the gas phase. So DFT HOMO-LUMO gap in the gas phase is 1.4 EVs. Now, when we do GW on gas phase COPC, we see that the energy levels obtained using GW actually agree well with photoemission spectra. And we get a GW gap of 4.3 EVs. So that's much larger than the DFT gap. And this is typical because the self-energy corrections tend to push the HOMO and LUMO further apart. Now, in the gas phase, we also have nearly spin-degenerate frontier orbitals. Okay, but when we have COPC on VSE2 and we do our XAFGW calculation, we find that we no longer have spin-degenerate HOMO and LUMO levels. We have spin-dependent tunneling barriers, and to understand this, we can examine the wave functions. The spin-up HOMO is more strongly hybridized with the substrate than the spin-down HOMO. And because it's more strongly hybridized, it's less localized on the molecule, and this leads to a smaller self-energy correction. So the self-energy correction for states that are more localized is larger. And self-energy corrections, remember, they push HOMO and LUMO away from each other. Now for the spin-down HOMO, we have a smaller interface hybridization and a larger self-energy correction for this state that is more localized. So the same thing can be said to explain the splitting of the LUMO that is observed here, that there's an interplay between interface hybridization and many-body self-energy effects. And this leads to a shoulder in the unoccupied spectra. Now again, we have beautiful data from the group of Professor Andrew Wee in NUS over here, and they also see a shoulder in the unoccupied spectra. And so this provides evidence of the physics of interfacial hybridization and many-body self-energy effects that I talk about here, which are also responsible for the spin-dependent tunneling barriers that we predict. Now, to confirm that it is due to interfacial hybridization, we can also do the XAFGW calculation, which remember does not take into account hybridization effects because it uses the wave functions from the COPC layer only, but it takes into account screening effects. Here we get a HOMO-LUMO gap of 2.6 EV and nearly spin-degenerate frontier levels as well. So in summary, this is actually quite a complicated system, and what determines the COPC HOMO-LUMO gap in this system? Okay, we can start with the gas phase COPC gap, which is 4.3 EVs. Okay, and the final gap for COPC on VSE2 is 2 EVs, which agrees well with experiments. Now, we can first consider screening from other molecules, which reduces the gap by around 0.3 EVs. Screening from the substrate without any hybridization, that's the XA-no-F calculation, reduces the gap substantially to 2.6 EVs. And then if you consider interfacial hybridization, the gap reduces more. Again, this is because hybridization reduces the localization of wave functions, which in turn reduces the self-energy corrections. Okay, So I have spent quite some time on this section for organics on 2D materials. So just to sum up, when we bring organics and 2D materials together, we can get new functionalities and improve properties. And one of the important features of these, properties of these, is the energy level alignment. And we have developed some approaches that can predict these energy level alignment in a tractable way that was not possible before, and also reasonably quantitative as well. Okay, so moving on, again, with 2 dimensions and 0 dimensions, I want to consider the interaction between two-dimensional materials and with the environment, for example, in O2 in ambient conditions. Now, in these cases, very often, these molecules tend to interact preferentially with defects in the material, as I show here. Okay, so defects in 2D TMDs, which I'm going to focus on, have been studied quite substantially, and it's quite well established that chalcogen vacancies are the intrinsic point defects with the lowest formation energy. So here I show some rather old STM images which confirm the presence of sulfur vacancies in MOS2, which is a prototypical TMD. But in my collaborations with Professor Andrew Wee's group looking at tungsten diselenide monolayers, we could not find the selenium vacancies. Okay, so here they have found 3 common defects, D1, D2, and D3, and none of these, okay, show any in-gap electronic states, which are predicted theoretically for selenium vacancies. And also, the STM images of these defects do not match with STM simulations of selenium vacancies or other intrinsic defects. So what happened to the selenium vacancies? Well, we predict that from DFT that O2 can actually dissociate at room temperature fairly easily at these selenium vacancies. And the resulting atomic oxygen can bind preferentially to the selenium vacancy and remove the gap states. Other possible binding sites are interstitial oxygen sites, as well as the oxygen at atom sites. Now, if we simulate the STM images of these oxygen-related defects, we actually are able to match well with the experimental STM images for multiple bias voltages. So this strongly suggests that oxygen-related defects are the predominant defects in these particular samples here. Now, why does O2 dissociate so easily at selenium vacancies? And the reason is the work function of WSE2 is quite small, and this facilitates electron transfer to the anti-bonding orbital of O2, which will weaken the oxygen-oxygen bond. And also this is confirmed by actually looking at the bond length. Even at equilibrium in the initial state is increased by more than 20%. Then you might ask, what about MOS2? Because just now I showed you some STM images of sulfur vacancies in MOS2. Well, the difference is that MOS2 has a larger work function. Okay, and as a result, because of the mechanism that I mentioned earlier, the energy barrier for O2 dissociation at the sulfur vacancy site is quite high compared to that of tungsten diselenide, and the estimated rate constant is orders of magnitude lower. So generally, we expect that chalcogen vacancies would be more easily passivated with atomic oxygen in WSE2 compared to MOS2. So what are the implications of this? We have 2 different types of defect behavior in the TMDs. Well, it has been observed in several papers that, generally speaking, WSE2 has a superior optical quality compared to MOS2. And also, there have been many papers published about single photon emission in 2D WSE2 rather than 2D MOS2. So we think that these features here are likely related to the fact that the chalcogen vacancies, which are the most common vacancies in the TMDs, are actually more easily passivated by atomic oxygen in WSE2, so that it leads to a better quality sample. We also predict that interstitial oxygen here is a potential source of the single photon emitters that have been observed in this particular energy ranges for the 2D WSE2. And we determine this from the fact that these are localized excitons, and they also appear in the energy range that has been seen in several experimental groups. Finally, we have also been studying the implications of this for the Schottky barrier heights in these systems, and we believe that the nature of the effects also has implications in this particular area. Okay, next we will talk about the interaction between two-dimensional materials and a 3D substrate. So this is a story about charge density wave states. So charge density waves are a collective state that appears in low-dimensional metallic systems, typically at low temperatures due to strong electron-phonon coupling. Now, usually the temperature at which a CDW state can be observed is quite low, and this actually limits the use for more practical applications. But my collaborators in NUS, the group of Prof Low Kian Ping, were able to observe the commensurate charge density wave state at room temperature when we have a 2H TaS2 bilayer epitextually grown on a hexagonal boron nitride bulk substrate. And this particular charge density wave state only appears below 77 Kelvin in the bulk material. Now, interestingly, this room temperature charge density wave state is not present if you have just got the TaS2 bilayer mechanically transferred onto the HBN, which is my short form for hexagonal boron nitride substrate. So this tells us that the specific epitextual relationship between the 2D material and the substrate is very important here. So to understand this better, we need to know the structure of this charge density wave state. It is a 3x3 supercell of TaS2, and there are 3 groups of sulfur atoms. In the group which I call S1, the sulfur atoms, they actually move slightly further apart, as I indicate with a plus sign. In group S2, they move closer together, indicated by a minus sign, and in group S3, they hardly move. And similar things can be said about the tantalum atoms. Now, so what's the role of HBN? A 3x3 TaS2 actually matches very well with a 4x4 HBN substrate, which I try to illustrate here, which is a substrate and some of the sulfur atoms. Now, HBN is actually quite an ionic substrate, and so it provides an electrostatic moire potential for this TaS2 that's on top. And sulfur atoms, they will have a net negative charge in TaS2. So the CDW phase is likely to be stabilized when these sulfur atoms in group S1, remember group S1 has the plus, sulfur atoms moving further apart, are actually close to this nitrogen atoms here, because nitrogen atoms have a negative charge as well. So the negative charge repels the negative charge. And likewise, if the sulfur atoms are close to boron, as shown here, these sulfur atoms tend to be drawn closer together, which actually corresponds to what is required for group S2 in the CDW structure. So indeed, when we examine the relaxed structures for TaS2 on HBN, we do see these kinds of patterns appearing. And S1 close to nitrogen and S2 close to boron. And these structures here, they appear from a total of 18 different starting configurations. Now, if we take any of these relaxed structures and we swap the positions of boron and nitrogen artificially, what we find is that the total energy goes up. It is not stable, and In fact, the stabilization energy for the charge density wave state reduces by half. So this confirms that it is actually the electrostatic effect here from the substrate that somehow magically stabilizes this TAS2 bilayer charge density wave state. And this is a very good example of how substrates, the interfacial interactions with substrates, can be used to tune the properties of two-dimensional materials, because the two-dimensional materials are only atomically thin, and so they are very susceptible to effects from the substrates. Okay, so in my final example, I will actually talk true to its name about a material where we have 3 different types of dimensions in one single material. So we have a romance of many dimensions. Okay, so this is a 2D covalent organic framework. It's experimentally synthesized in NUS a couple years ago. And it has 0D and 1D chain-like properties in a single 2D material. If we look at the band structure, it has an isolated flat band, which is highly desirable. And the isolated flat band is related to wave functions that are localized at what we call the bridge sites, which are 0-dimensional. And this is the lowest energy conduction states. The highest energy valence state is related to the 1-dimensional chains. You see the wave functions here, and they are slightly dispersive. So this material has some quite interesting properties. First, the isolated flat band, okay, is a good playground for many body physics. At least at the DFT level, we have tried to dope the system with electrons and found the onset of magnetism. We have also computed the Hubbard U and found that it's quite large, about 700 MeV, and it's a possible Morse-Hubbard insulator. But besides having an isolated flat band, we also notice, because this material has mixed dimensional physics, there is strong electron-hole asymmetry, and this leads to a large Seebeck coefficient as well. There's also linear dichroism and strongly bound excitons in this material. So perhaps with an improved design, we can even have a gate-dependent control of strongly correlated flat band physics and 1D physics in future. So from studying this material, we can actually understand some of the design features that go into creating mixed dimensional physics in a single material. And so covalent organic frameworks, they actually are usually built from bottom up and synthesized from molecular precursors. Okay, so the precursors in this case are I-shaped building blocks. And also something that's very important in covalent organic framework design is the connectors. Okay, so here we have the I-shaped building blocks and T-shaped connectors, which in the topology gives rise to these 1D chains and 0D bridges. So to optimize the effects, it's good to have perhaps longer bridge units as well as functional groups that can further isolate the bridge sites from the chain sites. Okay, so with this, I've come to a most important slide, which is my acknowledgement slides. So all this work would not have been possible without the hard work of my students and postdocs. So these are my group members, and I list them here in the order in which their work first appeared in this talk. I also want to thank my senior collaborators, also listed in the same order. The work on 2D metals 2D metals was synthesized by Josh Robinson in Penn State, and the ellipsometry measurements were done by Asala Wurzbauer in the Technical University of Munich. The DMAP OED project was led by Julie Cha at Yale University with collaborators Nilay Hazari and Hailiang Wang. And I also want to thank Andrew Wee from NUS, Steve Pennycook also from NUS, as well as Kian-Ping Loh from NUS. And I'd like to acknowledge my funding from the National Research Foundation, as well as the Ministry of Education in Singapore, and the computing facility support at the NUS Center for Advanced 2D Materials and the National Supercomputing Center in Singapore. And thank you very much for your attention.
Swing, thank you so much for the wonderful talk. I'm sure there will be questions. For the people who want to ask questions to Swing, please write your questions on the Q&A button at the bottom of your screen. Okay, so if you look at the bottom, you see a Q&A, you can write the questions there. So maybe I should ask you a question, Swing. So
Yes.
where do you see this whole field going? So you're already talking about putting together 0D, 1D, 2D, 3D. So what do you think is the next steps? What's going to happen next?
Well, I think one of the next steps that I see in terms of these 0D and 2D is actually in the field of quantum information. There's a lot of interest in these single molecule magnets, and we need to put them on substrates. And you see, I've already shown that when you put them on 2D substrates, the spin is actually retained, but when we put COPC on a box substrate, the spin is quenched. So I think there's a lot of potential here for quantum information applications, for one, in this field. And also in terms of the scope of 2D materials, I think when I do my work on a day-to-day basis, I'm quite surprised even with some of the new things that we find in 2D materials, and there are new 2D materials that are being discovered, for example, from these materials such as approaches and so on. Yeah.
Great. We have a question from Philippe Blasé. Do you use G0, W0, GW0, or GW calculations?
Okay. Typically, I use the G0, W0, which is a one-shot approach where we use the DFT starting point and we calculate the self-energies based on that. But in the case of the interfaces, we always do a check. We always check that so this G0, W0 approximation assumes that we have a good starting point so that perturbation theory works very well. So I always do a check to make sure that the off-diagonal elements in my self-energy are quite small, or if they are not small, I will do a rediagonalization and check the effects. So just now for the COPC on VSE2, if you notice, there was a solid line and a dashed line, but there wasn't much difference. And the dashed line was done with the rediagonalization.
Okay, another question from Philippe. Do you think the original XAFGW method you developed could be used for a 3D interface?
Yes, but it depends on the nature of the interfacial context. So here we show that the approximation works well even in the presence of hybridization, but we still need to be able to carve out a part of the interface from the other parts. In other words, we shouldn't have covalent bonds across the interface. Yeah. If you have covalent bonds, then that may be some problems. Yeah.
Okay. So a question from Xian Chen. Compared to the GW calculation, how much time we can save on a calculation using the XAFGW method? Thanks.
So if you want to look at time savings, we can only look at small systems, and I have some information on that. Theoretically, it's should be about order n savings. In practice, we get a little bit less than that, but that's for small systems. For the bigger systems, I cannot do this check because I cannot do the full GW calculation. Yeah.
Okay. Any more questions? Anyone? Okay, we are almost at the end. People know I always finish on time, so I want to thank Su Ying for talking today. Oh, okay, Stefan Roche in the last minute came up. So Stefan asks, molecules are likely vibrating in real conditions. Can GW be coupled to some extent with molecular dynamics or electron-phonon interaction effects?
Oh, that's a very good question. So the effects of electron-phonon interactions with on GW have been studied by some groups where they do it in steps. So they have a GW calculation, and then they have the electron-phonon calculation, probably at the DFT level, and then they couple them together. So it can be done. In my group, my efforts here are typically in looking at actually the 2D material enhanced Raman spectroscopy, which I didn't talk about here. And here we also need to look at the effects of electron-phonon coupling on the excitonic spectra. Yeah.
Okay.
So it is possible, yeah.
Great. Okay, folks, now I'm going to close. I want to thank you, Su Ying, so much for giving the chaos seminar today. And folks all around the world, stay tuned because we're going to have more in the year to come. I want to take the time to wish everybody Merry Christmas, a wonderful end of the year, and hopefully 2021 is going to way better than 2020, which was not a great year. So thank you, everybody. Happy holidays. Merry Christmas. Take care. Bye-bye.
Bye. Thank you, Antonio, and Merry Christmas.